So upper level wave and mid latitude cyclone, how's that the form? So to understand that, there are long wave and short wave, the length that wind flow. This one is zonal wind, another one is meridional wind. So meridional looping of the jet stream actually influence the upper level wave and mid latitude cyclone. So if we examine an upper level chart that shows almost the entire northern or southern hemisphere, such as you are watching in this picture, so the wave appear as a series of trough and ridges with a significant amplitude that encircle the globe. The distance from the trough to trough, or distance from the ridge to ridge, is known as wavelength. When the wavelength is on the order of many thousands of kilometers, the wave is called long wave. So at any one time there are usually between 3 to 6 long wave looping around the northern hemisphere, we can see. So the long wave are also known as planetary wave, and we call it Rossby wave more often because the Rossby is a famous meteorologist who actually carefully studied and this motion of atmosphere, upper atmosphere, and embedded the long wave. There are many short waves which are small disturbance and ripples that moves with the wind flow. So in here we have two types of waves, that's a zonal wave and meridional wave. So zonal wave is something that uh, move from east-west direction. There is no much distinct ridge and trough is here. On the meridional wind, sometime in the northern hemisphere, when polar vortex in the winter become a small weaker, then the north-south direction actually occur, and sometimes some of the air mass actually push all the way down to the south, and we get a lot of winter in the southern states. That happens sometime. So if we move there, if you're looking at the picture B, that long wave move eastward very slowly and short wave move fairly quickly around the long wave. So if you look at, you will notice that the short wave tend to deepen, that is increase in size, when they approach a long wave trough, and it weakens, become smaller when they approach to a ridge. So moreover, when a short wave moves into long wave trough, the trough tend to deepen, that's mean tend to increase. So where the contour line, now we will be talking about the barotropic situation. The contour line, if you're looking at picture B, that are roughly parallel to the isotherm, the dash gray line, the temperature is, the atmosphere actually is said to be barotropic. That's mean barotropic will be defined when the isotherm lines actually parallel to the atmospheric um, pressure line. Since the wind at this level more or less parallel to the contour line, in a barotropic atmosphere, the wind flow parallel to the isotherm. So by comparison, where the isotherm cross the contour line, temperature advection occur. That means this isotherm line, when cross the pressure line, the temperature advection will occur. And atmosphere, in this situation we called it baroclinic. So the baroclinic region tends to be in a narrow zone in the vicinity of short wave. If you're looking over here, 1, 2, 1 and 3, that short wave actually disturb the flow and accentuate the region of barosynclinicity. Yeah. In the region of baroclinicity, wind cross the isotherm and produce temperature advection. So when this isotherm cross the uh, pressure line, the advection happens. There are two types of advection: cold advection and warm advection. So cold advection, The cold air advection is the transport of cold air by the wind from the region of the lower or colder temperature to a region of higher or warmer temperature. In the region of the cold advection, when the cold advection happens, the air temperature normally decreases. So on the other hand, if we are talking about the warm advection or warm air advection, so warm advection is the transport of warm air by the wind from a region of higher or warmer temperature to a region of lower or colder temperature. So in a warm advection, warm air move to the colder air region. So normally in the region of warm advection, the air temperature normally increases because much air temperature move to the lower temperature region. So the cold advection to occur, the wind must blow across the isotherm from colder to warmer region, whereas the warm advection to occur, the wind must blow across the isotherm from warmer to colder region. So in the baroclinic region, if you're looking at picture B, so if you're observing that the strong wind actually cross the isotherm, and this is producing the cold advection. If you are looking at the blue arrow on the trough west side and the warm advection, which is indicating by the red arrow on its east side, so below the baroclinic zone lies the polar front. Above it flow the polar front jet stream, and this disturbed flow created and by the short wave is now capable of helping development of or intensification of surface mid-latitude cyclonic storm. So this theory explaining how this phenomena occur is known as baroclinic wave theory of development cyclone. So in here we need to make sure that we need to understand baroclinicity, barotropic, and the baroclinic, cold advection, warm advection,